Okay, sir. Fine. We can
Yeah,
start.
okay. So, very good afternoon to everyone. Special thanks to Jayakumar sir for again in the next series of this session on quantum. And now I'm just handing over this session to Jayakumar sir for the further discussion. Jayakumar sir, please.
Yes, sir. Thank you. Thank you for invitation. Let me share my screen. Is my screen is visible?
Yes, sir. It's visible
Okay.
from
Okay.
my end. Let the
Okay.
participant confirm on the chat box.
Okay. Great. Good afternoon to one and all present here. I invite you for QT-02 Foundation of Quantum Technology, and today's session we are about to cover quantum machine learning. Okay. We have demonstration also. We about to introduce one more software platform, Penny Lane, which is from Xanadu, Canada. Okay. So today's topic is quite challenging and difficult. Anyhow, let's cover very basic, very fundamental. If you are from CS and IT, most of you familiar with classical machine learning, so you able to correlate about today's topic. So let's start with the very basic question: what is a quantum machine learning, and where we can use quantum machine learning? So quantum machine learning is the combination of two aspects. One thing is quantum computing, the another part is machine learning. So if you really want to do something in quantum machine learning, you need to have a solid foundation about classical machine learning, what you already know. Okay, then you need to have the knowledge about quantum computing also. So most of the people they will ask how to convert their machine learning code, classical machine learning code, into quantum machine learning. It is quite challenging and very tough to convert during this transformation. Okay, so please focus on machine learning part, classical machine learning part, and try to understand as much as possible as quantum computing. Only few versions you are able to convert, not entire machine learning code. Only few machine learning models you are able to convert into quantum domain. Okay, and also it is very challenging and is not um, uh, uh, promising. The result is not as equivalent or surpassing to classical result. Okay, we need to wait for some time. Maybe after 10 years, 15 years, it can beat classical machine learning. So far, classical is best, but in future, quantum able to complete or compete. The idea is combined concept from machine learning and quantum computing. Okay, so whatever you have your classical machine learning code, you need to convert and you need to execute in quantum machine. So if you do simulation, definitely quantum machine learning will not give a clear advantage. So we need to execute on quantum machine. Then only you will have certain advantage. Is my audio is clear? I hope. Is my audio clear? Great. Thank you. Okay. So whatever, if you have a classical machine learning code, you can try into quantum version or quantum inspired. You are able to load into quantum machine. Then it will execute and give back result to your machine. Okay, so what happens during this process, it will learn pattern and it will get relation from given training data as equivalent to classical machine learning. So the only difference is it will use quantum mechanical resources to solve computational problem potentially more efficiently or accurately than classical computer. So whenever if you are thinking about, if you want to go for quantum machine learning, you need to ask so many questions, so many parameters. So if your given problem is more suitable, then only go for quantum version. Otherwise, please stay in your classical model. So this is the overall idea. It is the culmination of both machine learning, quantum computing, and optimization technique. If you are looking at a combination of optimization and quantum, it will lead to quantum information processing. Information processing. So if you have a very good quantum computer, right, and if you have a very good classical machine learning, then it is possible to do big data processing. So far, it is impossible. Okay, quantum computers in today's scenario, it will support very less number of data set. Okay, very less number of sample or very less number of input size. So you need to remember. So immediately, if you are pumping a large amount of data, your quantum computer will fail. Then if you have optimization technique and if you have machine learning, then you can produce intelligent algorithm. Okay, the combination of all this stuff will yield to quantum machine learning. So it is near future. So far we are playing with some toy model. Okay, right now quantum machine learning will not able to compete with classical machine learning. So this is the fact, true fact, you need to keep in our mind. Okay? So with the help of quantum machine learning, what you can do or what we can do. Okay, you can do drug design, you can predict new materials, and you can speed up simulation if you're using quantum simulation. Otherwise, you can use classical machine learning code and you can enhance that operations. Okay, so it is not just about quantum machine learning, even you can improve the classical machine learning also. Okay, this is also possible. So in future, if most of the sensor will turn into quantum version, the input will be accurate. Then if you are using actual quantum computer, we cannot believe we can have very high accuracy in meteorological departments as well as healthcare. So whatever we are doing, it is not nano level scaling or quantum level scaling. Okay, so in future we will treat diseases in very personalized way. So quantum computer will act like AI accelerators. So this is the first point. Okay, so it will complement whatever the AI model already exists. Okay, so you can define quantum machine learning in different way. It is a research area that explores interplay of idea from quantum computing and machine learning, right? So by extends the pool of hardware for machine learning by an entirely new type of computing device, which is called quantum computer. Okay, so normally if you are doing simulation, you cannot expect the desired output or desired advantage when it execute in quantum computer. So simulation, uh, we cannot get that much of accuracy, right? So we already know all this stuff, we can skip. So right now in 2025, we are using uh, fault tolerant QPUs. Okay, this is the universal idea, but it will take nearly 15 to 20 years to happen. Okay, so right now we have noisy model, right, which is called NISQ. Okay, noisy intermediate scale quantum level. It is like a toy robot. So look at the image. It need to grow and evolve year by year by a robotic revolution. Okay, more and more sensors, more and more capacity. Then this is the expected fault tolerant quantum computer or fault tolerant quantum machines. So nearly, if you want to achieve FTQC, we need to wait for nearly 15 to 20 years. Then your quantum machine learning will have over advantage over the classical machine learning. Okay, so until we are doing with toys problem. So what you can do with the help of quantum computer, it will behave like a neural network. So most of us, we know about neural network, how we can use that, how we can train that. In the same way, the quantum computer can be used like a extended neural network or super neural network. Okay, so systematically we can control and adapt physical parameters. Okay, such as an electromagnetic field strength or laser frequency to solve a problem. So we are believing physical quantity. So this is the beauty when compared to classical computation. So classical computation is about everything is about software, logical, but here we are dealing with physical quantity and physical signals, right? So for an example, a trained circuit can be used to classify the content of images by encoding image into physical state of the device and taking measurement. So in classical, what we do, everything will convert into binary states. But here we are able to convert into quantum states. So directly, if you have quantum signal, you can feed into the system. Otherwise, we need to encode the classical image, okay, classical binary data into physical state of your device. So again, we need to have superposition, and we need to construct quantum circuits, and it will go one of the states. So like the previous lectures, everything is based upon quantum principles. The bigger picture is you can do programming in very differential way. So it is not a static programming or dynamic programming. It is a differential programming. Okay. So all quantum circuit are differentiable. In last session, we covered about block sphere. In block sphere, am I audible? Yes. Thank you. Thank you. Fine. So quantum circuits are differentiable. So what is the meaning of differentiable? You able to differentiate your circuits, you able to differentiate input and output sequence so that the quantum computer can itself able to control the parameter. Please go to the YouTube channel. They have recorded videos. Okay. So this is your circuit. Your circuit contains various alphabets like alpha and beta, right? And you can able to fine tune this alpha and beta. So this is the beauty your quantum computer is able to do by itself, uh, by changing those variable, able to calculate the optimized cost. So most of the problems in classical, uh, uh, the complexity is increased when there is a randomness. Okay, when there is a random guess or random process. Okay, or combinations. So those type of problem exactly suitable for quantum machine learning. Okay. So differential programming is very basis of deep learning. So if you know differentiable programming, you can have very powerful deep learning algorithm. Okay. So most of the differential programming, okay, it is more than deep learning, and this programming is not hand coded but learned. So it is like a combination of reinforcement learning. Your quantum circuit will learn by itself. Okay, it will fine tune the parameter over each and every iteration. So this is the basic idea. So whenever if you have a trainable quantum circuit, okay, so you can use those circuit for quantum chemistry or quantum optimization. So normally the classical algorithm will fail because the user need to fine tune parameters, okay, which is very time consuming, and we need to do lot of trial and error. But in quantum, the circuit itself able to train because it always want to settle down the minimest energy, the lowest possible energy. Okay. So if you able to develop such a kind of application, okay, if you have more and more quantum error correction schemes and understanding a physical system, then we are able to design quantum algorithms, better quantum algorithm. In between, I will read few comments. Why lower energy means in quantum there are two energy levels. One is the minimum energy, the excited state. So almost in universe every particle tends to be spin lowest energy. So this is the basic nature, okay, of all quantum particle. So for an example, why we are looking for the promotions, why we are looking for all appraisals, why we want to go for higher level states. Once you reach that states, then everything will be easy in your life. Okay, to do anything, you have a lot of power, you have a lot of control. It is easy for you to explore all possibilities. So whichever how to put in the word. So whichever organism, okay, play at the peak level or apex level, it will do everything at ease of cost or very less minimal energy. Yes, we will consider. So wait for a few more topics. So now we have faulty quantum computers. We have so much of noise. Okay, the fault tolerant is able to surpass those errors, those noises. This will take 20 years. So what we can do, we can look for near-term quantum processor. So the first part will take 15 to 20 years. Okay, the second part will be available within 5 years. So if you are using quantum error control version, you're able to achieve near-term quantum processor. So most of the institute look for near-term quantum processor. So fault tolerance is very difficult. So many qubits to enable error correction, more likely to find provable advantages. Okay. So all these examples of QML, are related to fault tolerance. So I'll share all this link with you. Whenever if you got time, please go and refer this reference, right? What is near term, which is already existing quantum hardware, okay, which is already existing quantum hardware. This error will cause due to physical noise. So we cannot completely avoid or ignore physical noises because it is inherently exist. Even though if you are using the isolated system, even though the noise will exist intrinsically. Okay, so if you have near-term quantum processor, what you can focus on quantum kernels, quantum GAN, and quantum Boltzmann machine. So many algorithms are possible in near-term quantum processors. Okay, so I gave very few examples. So it contains both good news and bad news. So let's start with good news. So what quantum computer can represent complex structures which is not efficiently accessible by classical computer. So if you want to focus on some quantum machine learning model, first of all, you need to understand whether it is really not able to executed by classical machine. It requires the exponential resources. Then you can go for quantum machine learning. Okay. So take an example of a classification. Okay, this is the basic classification ABC. Okay, if you are using training data, okay, you're able to build your model with the help of test data. You're able to test whether your built model is efficiently able to classify or not. Okay, so sometimes you can have a misclassified test data which will lead to error. Okay, the same process we need to do in quantum computer. So whatever you do in classical machine learning model, this same step, same procedure we need to follow for quantum also. Okay, the most important point, okay, whenever if you are looking for quantum machine learning algorithm, the first point you need to map your data into exponentially large state space. Okay, so this will give a clear advantage for you for a very quicker process. Okay, so take an example of number of stars or number of particle exist in this universe. Okay, If you have 275 qubits, okay, you are able to represent the entire atoms exist in the observable universe. So no supercomputer, if you combine all computer together in this world, it cannot beat a 275 qubit system. Okay, so imagine how much data you are able to represent in your quantum system. But only thing, all these qubits should be noise free. So that is the trick. So today we achieved almost 1000 qubits, even though those qubits are noisy. Okay, so there is a basic calculation. There is a basic calculation. If you want to achieve one good logical qubit, say error free or noise free, error free or noise free, you need to have 1000 physical qubits. So this is called fault tolerant. So it is very difficult. It is very difficult. That is why IBM is aiming for million qubits and 10 million qubits. Okay, so they have this plan. Then only quantum machine learning is efficiently possible. And what is the bad news? Uh, Loading your data and reading your data from the system is very challenging and very difficult because the RAM is not available. You cannot store quantum information. So memory is very biggest problem in quantum computer. So memory is very cheapest in classical. Okay, even if you are paying a few hundred rupees, you are able to get the pen drive of 1 GB or 2 GB. But in quantum, the RAM is not available. You cannot store your data. Okay, so whenever if you have quantum system, okay, what is the bottleneck? Loading your data. Okay, reading out your data become tough. So this plays a crucial role, which is blocking to implement quantum machine learning. So loading data and reading data is very easy in classical computing, but in quantum quite difficult. If data grows, okay, data size is so much, you cannot store. You can store, but each and every time we need to load, we need to process. We need to process. Again, if you are loading, all quantum information will get lost. Okay, everything will get refreshed. That is the problem. So try to understand in very simple way. So what you can do, you can use a parameterized quantum circuit. So if you have a quantum circuit, you can go for the second option. Each and every time you can parameterize your quantum circuit, but it is very difficult to train. Each time if you change your data, all your quantum state also get changed. Okay, because it is due to vanishing gradients. So if you are looking for particular pattern, if you keep on move, everything will change according to which point if you are looking. Okay, so what we can do, we can employ classically as well as we can employ quantum resources to outperform traditional approaches. So it should be hybrid. So normally we cannot entirely believe on classical, we cannot entirely believe on quantum to solve a toughest problem. So we can go for hybrid approach. So how much it is possible, you can do at your classical end. Okay, only for certain part or crucial part, you can go for quantum machine learning. Okay, so analyzing this and picking the right problem is very tough. Again, we need to have so much of knowledge. Okay, it will take lot of time, right? So let's have a quick comparison about machine learning So for machine learning, we need to have data and we need to train our model, right? Then we can predict some cost function. Okay, by using data samples, we can able to construct the model, and it will provide the minimized cost. Whenever if you are giving a new data, okay, the execution or prediction should contain minimal cost. So this is the ultimate aim of all machine learning model. Okay, the process should have a very minimal cost. If you are doing in linear model, okay, if you're doing, cost means how much resource it is consuming, how much time it is consuming. So that is what normally cost. So if you're using linear model, with the help of a straight line, you're able to classify your data sets. Okay, then you can use some convex optimization in order to fine tune your linear model. Suppose if you're using kernel methods, you can have a curved line in this way. It is not a straight, but you can divide a random fashion of your data set, okay, in much more comprehensive way with the help of convex optimization. So in both linear as well as kernel, we need to use convex optimization. Okay, fine. So if you're using deep learning, so what happens here, the amount of data is somewhat big. So we tend to go for big data model. Okay, in the model, it contains so many layers, and these layers are composable and also differentiable. So that is why if you design a differential quantum circuit, it will go the enhanced version of quantum deep learning. So this is more suitable, okay, or more reliable. If your model is too complex, if your data is too complex, then you need to go for non-convex optimization. Okay, so multiple parameters are required, like gradient descent and high performance hardware and special purpose software. If you have all these stuff, then you can easily achieve, not easily, you can able to achieve non-convex optimization. So in this way, how quantum computing will help? So if you want to use your data, you need to use fewer data samples because it won't support big data, okay, right now. So we need to always use few data samples. So that is why please always remember, if you want to implement QML, you need to focus on toy problems. You need to focus on toy problems, not real world real world uh, um, real world problems. It will take much more time. So quantum cost is nothing but how many qubits required to, how many number of qubits required to implement your circuit. So this is what normally quantum cost. This is the rough. So we cannot decide simply qubits. They will say quantum volume. Quantum volume. So this is the parameter established by IBM Quantum. So if you have time, go and refer IBM Quantum volume. Maybe I will share some uh, reference. Very good question, actually. IBM Quantum volume. So I'll share this link with you. Please go and check what is this quantum value means, right? So most of the quantum industry accepted this metric. So if you want to measure the quality of quantum computation, we need to measure with the help of quantum volume. So it comprises multiple parameters, not a single parameter. So sometimes 100 qubit system can easily dominate 1000 qubit system because architecture different, the way it process different. So we cannot normalize. So this is very challenging in quantum scenario. Okay, then we need to process quantum data. So we need to have we need to process that quantum data. Then we need to do optimization. Okay, so as like classical, in some cases the speed up will happen. Okay, then we can go for new design models. So I gave all these references. Please go in your free time. Okay. So you can compare quantum circuit like a neural network. You are able to train if you have very big model. If your circuit is composable and differentiable, then you can go for non-convex optimization, right? Suppose if you have a physical circuit, okay, consider this is a quantum function, you're able to encode your input data. So this is your input data. What you have to do, so consider this is a binary data. So binary data you need to encode with your quantum function. Okay, then you need to do some quantum processing, then you need to do measure. So whenever if you do measurement, your data is again converted into binary form. So where is the advantage? The advantage exists in the processing because everything will happen in quantum domain. So input also classical form, output also classical form. Right. So beneath I gave mathematical description. So you will have all this information in Penny Lane website. Okay. So in Penny Lane, what we supposed to do, we need to create a classical node and we need to create a quantum node. So quantum node depicts number of qubits or bunch of qubits. So this will take care about your entire circuit. Okay. So quantum node is nothing but your quantum device. So you can do in multiple ways. Either you can use a class simulation or you can execute quantum system. So Penny Lane having collaboration with multiple vendor. Okay, you can execute the same circuit in Amazon, in IBM, in Microsoft or Google quantum systems. Okay, so this is very good for us. So I'll skip all this slide. Okay. So consider your quantum models are similar to kernel methods. We already have some idea about kernel methods in classical. So you can compare all these quantum model similar to kernel models. So depends upon the location, you are able to form the kernels. Okay. So again, the same method, you're able to do either non-convex or convex optimization depends upon your problem. So take look an example of classification. So if you are using classification, we are able to identify whether it is authorized mail or spam. If you identified as a spam, then you can move to your bin. So based upon your previous classical data, your model able to classify. Okay, so you can apply all these things to a customer group if you're able to classify. Okay, so you can do learning from the video game. So you can create a machine learning model. So looking at the object, able to identify some pattern, right? Then subsequently you can move to generate images, generate text, like generative intelligence. Okay, everything is built upon a model which is able to learn its own pattern. So most of the time what we are doing, we try to build a model which is able to learn through some patterns. Okay. Suppose if you have data x, and if you're building a model f of x with some parameter data, okay, here we are referring to data angles, okay, then you will get some output. So x tends to be y dash or y hat due to some changes in your system, right? So based upon this basic model, you can implement supervised learning, unsupervised learning, and reinforcement learning. So already we know all this stuff. I'm just giving for a glance, right? So in supervised learning, you try to understand the given example with linear function, then you're able to predict whether the mail is spam or not. In unsupervised, if the data is unlabeled, then you can use quantum circuit to create cluster. So today we're going to see about a variational cluster as an example. So reinforcement, it requires a lot of functions, lot of layers. Okay, it will have a densely packed neural network to identify each and every uh, object in your model. So whenever if you do this, okay, you cannot achieve the expected outcome. So sometimes you will have loss, okay, sometimes you will have error, okay. This is considered like loss, okay. So whenever if you have error, whenever if you possess loss, then what you do, you need to do refinement. You need to update your model. You need to update your model. So again, this is like trial and error. So like trial and error, each time if you do, your output model will get improved. Suppose if you are using supervised model, you are able to control your data. You are able to give the label data. Okay. So if you are giving y of I equal to 1 to represent cat, then you can represent y of j equal to -1 for a dog. So you are helping your model with distinguished labels. So this is what called supervised learning. So if you are giving the better input, if you are giving better input, better future with proper label, okay, so your model able to understand all these parameter. For an example, what is the length of your tail, what could be the weight of your object, or weight of a cat and weight of a dog, or volume, okay. So it will able to understand, it able to get training, okay. Suppose if you are giving some test data, and it able to identify the given new input. So normally what we'll do, we'll take 80% for training set, 20% for test set. So these basics we already know. Okay. Again, I will skip all these basic things. Fine. Suppose if we have one new data, okay, if we have one new data which is not classified, if you are doing testing, okay, so depends upon the output, you need to give feedback for your system, whether it is correctly classified, you need to give some feedback so that you can improve your system. Okay. By doing this regressively over and over, at some point of time, your model become more accurate. Your model become more accurate. So consider the previous examples and basic theory. Now we are looking for quantum machine learning classes. So it contains 4 models. Okay. So classical data with classical processing, quantum data with classical processing, classical data with quantum enhanced processing, quantum data with quantum enhanced processing. So there are 4 different types of quantum machine learning you can do. Okay, so this is purely classical. This is purely classical. These two are hybrid because we are mixing data with system, right? This is purely quantum. So in 4 combination, you're able to implement quantum machine learning. Okay. The first two will represent for mostly support vector machines type. The last two will represent for quantum support vector machines and variational quantum classifiers. So if you go more with quantum, more difficulty will come to implement. Okay. So what is the advantage of going for quantum machine learning? The only word, quantum parallelism. Okay. So quantum parallelism have the massive advantage from superposition. Okay. Within a single qubit, you're able to represent multiple level of information. Again, it is constrained to what logic if you are using. Okay. So with 2 states, you are able to represent, sorry, for 2 qubits, you're able to represent 4 quantum states. Okay. When in case of classical, it will execute one by one. It will execute, sorry, it will execute one by one. But if you're representing 4 quantum states in a single qubit, you can run parallelly. So within a single shot, you're able to execute the entire combination. So that is why quantum have advantage. But again, the number of qubits are limited. The quality of qubit is very poor, prone to noise. Okay, that is why we are not able to have the advantage, pure advantage. Again, I will skip all this slide. I already defined. Okay, so let us discuss if you are using CC, so classical computer and classical data, but your algorithm could be inspired from quantum computing. Suppose if you have already classical machine learning algorithm, what you can do, you try to improve that algorithm. You try to improve that algorithm using quantum principles. So this is very easy, very easy. And you are able to implement quantum inspired algorithm within 5 or 6 months if you are focusing. Okay, even in your classical system you can run quantum inspired algorithm. The second type is CQ, where you have classical data and you can use quantum machine learning algorithm. You can use simulator. You can use simulator maybe in classical machine or HPC, be able to achieve CQ. Okay. So the third type is quantum data and classical machine learning algorithm. And here there is a trick. There is limited amount of quantum data. Limited amount. So I will give a very good repository for quantum quantum data set. Again, the data set available in Penny Lane. I will share this link with you. So here you can download few quantum data set. You cannot expect like classical, like Kaggle. Okay, only few data set you able to access. Okay. So I will explain what is the use of QC. What is the use of QC? Quantum data with classical machine learning. You are able to improve the algorithm for quantum computing. You are able to improve the qubit quality. You are able to improve the control of your qubit. Okay, then you are able to improve the output from your qubit. So all this stuff you able to improve. So this is mandatory to improve quantum computing. Improve quantum computing, or you can say quantum volume. So this determine quality of your computation. So as we discussed previously. Okay. So it is like quantum supporting for itself. Okay, through classical machine learning. So that is why it is a hybrid approach. So this is very good if you are doing. The impact is so high because you are improving quantum system with the help of quantum data. So this is more natural, right? The last one is QQ, where you are using quantum data for quantum machine learning. So this is very interesting, and this is have very high advantage, very high advantage when compared to all these three. Okay, because we are properly using quantum data, we able to do with quantum machine learning, and be able to implement in quantum computer. If you do so, you will have very good accuracy and very high speed computation. So next, how we can categorize our quantum algorithm based upon two distinct category. So one which requires quantum random access memory. Okay, this is very synonymous to RAM, but it is not like that. Okay, uh, if you want to store quantum data, it will stay few milliseconds. Then imagine how fragile your system is. So even though we are using quantum system, okay, because whenever if you're feeding data, if you're loading your data, it will turn into quantum state, and it will be considered like superposition. Superposition will stay for few milliseconds. So before it decay, you need to do all your computation. So that is why quantum memory is quite challenging and very very limited. Okay, so if you have QRAM in future, if you have QRAM, you are able to implement QPCA, principal component analysis, QSVM, clustering. It will speed exponential way when compared to classical algorithm. So maybe in future, okay, if we have QRAM, we can expect. So all this classical algorithm will turn into exponential speed up. Okay, so this is the problem. So right now, currently, there is no viable hardware candidates for releasing QRAM. So whenever, if you want to do process, if there is so much of storage, so much of data, please don't choose quantum ML. Okay, quantum ML will fail. So maybe I will skip all this data. This is the broader classification of quantum machine learning algorithm. So I try to classify with the help of my teammates. So this is what I got. So this will give a overall idea. So already if you are working on some algorithm, you can look for the particular domain. So this is the topic we are looking for, variational quantum circuits. So each and every time we try to vary our circuits. Okay. So how it is constructed, if a family of structured circuit is sufficiently random. Okay, how it could be sufficiently random by implementing Hadamard gates. one by one, and by tweaking their parameter, definitely I will share all these resources. So please wait, end of this video I shared all this link. Tweaking their parameters can explore a large region in the space of quantum states. Okay, so majorly we need to use Hadamard gate. So if you do so by optimizing the parameter choices suitably, we are measuring the resulting state, we are able to obtain classifier, function approximator, and regressors. So in such a way, we finally able to do quantum machine learning. Okay, so we don't know how successful we are so far, but we able to try. So in short, in nutshell, if I want to say, quantum machine learning, it is in baby steps, evolving step. So directly we cannot compare with classical result, classical performance. So how to do variational quantum circuits by using parameterized circuit? Then we need to do parameter optimization. So this part again you can use classical computer. So each time it will do parameter optimization, it will give feedback to your quantum circuit. So that is why this quantum circuit is called variational quantum circuit. Okay? It will evolve by itself if you are giving the proper feedback. So these are the important four categories: QML, VQ, VQE, VQLS, and QAOE. So these four types, majorly you can look into recent publications. So most of the variational circuits is based upon gate based. For an example, if you want to discover a new material, okay, optimization, even Boeing, IBM, ExxonMobil, Dilemma. So all these corporate are using variational quantum algorithms, okay, which is gate based. So it is not only for material, it is used for bioscience also, right? So they are using variational quantum algorithm to treat cancer treatments, to discover biomarkers. So which are all the biomarker responsible for cancer, okay, responsible for cancer. So all these problems are toy level, okay. So even it will take 10 to 15 years, okay. They are doing toy level problem. So I gave various example. So in your free time, please go and explore all these references. So again, I classified important quantum algorithm maybe in QT-03 or QT-04, we able to cover all these algorithm. So all these algorithm have respective QML applications. So this is a rough idea. Okay, so if you want to do quantum machine learning, first step, we need to convert classical data into quantum data. For that, we need to set up environment. We need to load data set from repository, just like classical. Uh, uh, then we need to do pre-processing, normalizing. This is the tough part. We need to convert the classical data into quantum data using so many techniques. We can do encode, but you can do encoding in multiple way. Okay. Then we need to do parameterized circuit. We need to add optimizer. We need to train circuit. Finally, we need to do measurement. So measurement will not come in classical part. Okay. Training will come, then testing will come. Here there is an additional process we need to do measurement. So this is actually uh, opposite to encoding. So whatever you encoded in binary form, okay, you need to decode. So this encoding and decoding, the quantum programmer need to decide. Okay, this is the developer perspective, how you need to encode your data, how you need to decode your data. So take an example of encoding in classical machine learning. We call it as feature mapping. Okay, so each and every classical data you are able to convert into quantum states. We already discussed what is a quantum state. Okay, so there are three encoding basic techniques. You can use angle to encode, you can use amplitude to encode, and you can use circuit to encode. So three ways you are able to do. Okay, so depends upon the problem statement, we need to choose our encoding. So again, this is challenging. We are doing trial and error. So each and every time it will vary. So Hamiltonian, I hope already covered in QT-01. So please go and refer. It is a mathematical definition. This is very different method, ansatz, different from gate based. So whatever we covered in previous lecture, it is about gate based, but ansat is entirely different. IonQ is a company. IonQ is a company. They are using ansatz. Okay, so for that we need to know Hamiltonian of a quantum system. It will evolve according to the time. Okay, then we need to search for ground state, minimal energy. So more frequently you will hear Hamiltonian and ground state. Okay, so this will give a clear advantage in quantum result. Okay, this is quite challenging. That is why you can look for alternative hardware efficient methods. Okay, so if you are using a quantum system, you need to check the topology of your qubit. You can check your topology of qubit. I can give a fair guideline. Topology of IBM qubit. So take an example. Take an example. So this is your qubit architecture. Imagine this is your qubit architecture. It contains nearly 5, 6, 7, 10, 11, 13, 15 qubits. Consider 15 qubits. These qubits can be organized in any geometrical shape. Okay, so each and every qubit have some specific property, specific error. Okay, so in such a way, if you are organizing qubit to yield maximum output, then your quantum circuit will behave differently. So the quality of your qubit indicated by this color. Imagine this 18 qubit have most prone to errors. So the quality of qubit is too low. Okay, so what you need to do, you need to customize the quality of qubits next to next. In such a way, you are able to suppress or reduce your qubit noise. So this is very different. Okay, in classical we don't have any this kind of problem. So all bits are equally having the same quality. Okay, but in qubit, each and every qubit differs in the property, differs in the quality. So this is one kind of example I could say. So hardware based, hardware efficient method is much more easier when compared to problem inspired method. So in today, we're going to discuss about building a variational quantum classifier with PennyLane. Okay, so PennyLane is a company. It is a open source framework supported by Xanadu. Okay, which is a Canadian startup. Okay, we about to uh, harness the quantum circuit for supervised learning. So this is the given example. Okay, so I will reiterate once again the variational quantum classifier. So what is the variational quantum classifier? It is a hybrid model. So combining classical circuit with quantum circuit with classical optimization to perform classification task. So this is our objective. So this is our objective. Okay. So by using this variational quantum classifier, we are able to learn the decision boundaries. The decision boundaries given from the label data. Right. So what are the key components we need to know? We need to do data encoding into quantum states, and we need to use parameterized quantum circuits. Okay, so this will give the better predictions if you do measurements. So you will get output only after measurement. Okay, so again I will reiterate, whatever we do with quantum machine learning, we are doing at toy level. Okay, basic level. And each and every time what we supposed to do, we need to use classical optimization to improve circuit parameter. So each and every time we are varying the circuit parameter. So that is why it is called variational quantum circuits. Sorry. That is why it is called variational quantum classifiers. So the first step is data preparation. The data set is given. So in this demo, I will provide the data set. Okay, I will give the training set. So synthetically, we need to do binary classification with the help of SkySet, scikit-learn. And what is the pre-processing? We need to do feature scaling, okay, for normalization purpose. So that we are splitting the data into training set and test set. So training will conquer for 20%, test will conquer for 20%. So simply what we are able to do, we able to give the label either 0, 1 to -1 or +1. So each time if you do measurement, so this is your input data set, this is your output measurement basis. Imagine if you have a circuit S of x that is mapped into classical data x into quantum state. So this is how your circuit will look like. So your S of x exactly mapped to classical data x. Okay. So which will lead to quantum states. So first of all, we need to encode our data. We need to do mapping. Okay. So each time the circuit U of data able to change with parameter data. Okay. So whenever the parameter data changes, this U of data also changes. So again, this will have impact in your process. Okay. So whenever you do measurement to the first qubit in the computational basis, you'll get expectation value. Okay. The expectation value serves as model's prediction, which is compared against true label during training. So during training, we need to compare with expectation value with the output generated by the system. So if you want to do the same scenario in penny lane, you need to set quantum device. Okay. So by default, penny lane will use simulator. So you can change into quantum hardware also. So if you wish, okay. So in today's example, we use simulator. The next thing we need to construct circuit. Okay. For that, we need to have Q node. So this is like a data structure. This is like a data structure. We already covered in previous slide. Please go and check that slide. Okay. So each time what you do, you are applying rotational gates. So yesterday we covered, sorry, in last session we covered Rx, okay, Ry, Rz, these are rotational gates. These are rotational gates. So we need to use all these rotational gates, okay, and entanglement to set parameter for data. Then what we need to do? We need to use classifier function. Okay. So each time we need to compute what is the circuit output, what is the bias it produced. So any deviation is there, you need to refine your circuit. So the first part, we need to do optimization. So you can use gradient descent method, which is already used in classical. You can use the same function to use minimal function loss. Okay. What is the meaning of function loss? It is the mean squared error between predicted and actual labels. Okay. So we need to run this program, run this execution multiple times until your parameter data is improved. You are getting classification accuracy. So until that, we need to do iteration. Okay. So once you identify decision boundary, once you are plotting your classifier's decision boundary over your feature space, you can stop and you need to evaluate about your training and test data set. Then you need to measure, then you need to observe between the classical and quantum version. Okay. So I'll hold this slide. I'll hold this conclusion. Now we go for Penny Lane website. So please go to this website. I already shared in the chat box. So this is the website dashboard. So go to demos. Go to demos. So you can see variety of demos. So this is only filtered to QML. Okay. So this is only filtered to QML. You can look over here. In QML, you can choose variational classifier. So actually it is like a tutorial. So you can self-learn this tutorial at any point of time. Okay. So in this example, we try to emulate parity function. So parity function is if you're giving some input, so based upon your output, you're able to say whether it is evenly having one or uneven. So I'll share that Python code also. I'll share that Python code. So please download this Python script. Okay. So go to your QBrate. Go to your cube, So launch lab. Am I audible? Are you able to follow? Okay, thank you. So what do you do? Go on add environment. And look for penny lane. Version 0.34.0. Look for add environment in QBraid, penny lane version 0.34.0. Please follow my chat box. Try to install the kernel. Okay. After installation, you can see option like this, Python 3 penny lane. No issue. You try to install. Let's see whether it is working or not. So click Python 3 penny lane. Maybe I will zoom for your convenience. So what is the first task we are doing? We are fitting a parity function. Okay. We are importing all penny lane library. Okay. So click this code, click here. Okay. Go to your Jupyter notebook. No issue. You watch this video after. If you are getting free time, go to YouTube, follow these steps. Straightforward. So click over here. Okay. Start to run. So we loaded all libraries related to penny lane and NumPy. Okay. Next, what we need to do, we need to create a quantum device. So here we are using simulator. Okay, even though we call it as quantum device, we are using simulator. So copy this code. Try to execute over here. Check what this device contains. It is created. So if you have doubt about execution of your code, just try to print that object. So what is happening? we are importing Pennyline library. Okay. Then we are importing NumPy library. Then we are importing optimization function optimizer. Okay. In cell number 2, we are creating a device which is default qubit. So if you are using a real-time hardware, you need to change parameter. Suppose if you are using IBM or Amazon or Microsoft quantum computer, you need to change. Okay. So if device is available, then they will allocate for you. So again, it is based upon the condition and constraint. Scroll down. Okay. So next, what we need to do, we need to add parameters. We need to add layers. Okay. Then we need to add weights. So this concept is borrowed from classical machine learning. So in cell 4, what we did, we define the layer. We are getting layer weights and we are creating wires, number of qubits, and we are importing all these weights to these qubits. So all these weights, okay, operated by rotational gates. So this is what it means. So these are qubits, number of qubits. Okay. So basically we are creating 4 qubit system. Then what we are doing, we are connecting all these wire with the help of CNOT gates. So this is your classical data, x equal to 0, 1, 1, 0. Okay. Then you need to convert like a quantum state. Simply you can encode with the help of basis state. So this is the function. Okay. So how to convert into basis state? With the help of state preparation function. Okay. So next what we are doing, we are defining quantum node. So for that, you need to use all your circuits, weights, state prepared. Okay. Then you need to put all your layers together. Then you need to return the entire thing like a poly Z gate operation. So if you are not able to follow, don't worry. This tutorial have self-explanatory. So in your free time, please go and read. I am using the very simplest QML demo. Okay. So maybe I'll use this. So what we did so far, we imported all Pennyline libraries. We created a device. So here we are creating default qubit, which is simulator. Okay. Then we are adding layers. We are adding weights to it. We are creating number of qubits and we are assigning weights to those layers with the help of rotational gates. And we are adding CNOT gates and we are interlinking all these qubits. Next, what we are doing state preparation. How we are preparing state preparation? With the help of basis state function. So this will assign what are the weights you assign. Okay. So all those weights connected with your qubits. So this is how your input is converted into basis state. Okay. So next we created a circuit. So according to the number of weights, according to the number of layer, we are able to compute Pauli Z and we are returning the whole expression. The next part, we need to do variational classifier. So here what we are doing, we try to compute weight associated with input along with bias. So whenever if you run the circuit, it will have some bias at the end. So according to your bias, you need to readjust your weights. So far, so good. Now we try to calculate cost function. Okay. So cost function is normally a sum of loss function, or it will act like a regularizer. Okay. So normally we are speaking cost related to standard square loss. Okay. It will measure the distance between targeted label and model prediction. So this is the error. Okay. This is the error which will happen in your prediction. If error is less, the cost is also less, right? So next what we do, we try to define accuracy function. So from different kind of labels and different kind of predictions, we able to identify how much accurately we able to classify or categorize. So next what we do, we try to define cost function. We try to define cost function. For each and every cost, we are giving input for variational classifier. Okay, this is the classical classifier. We are using classical computation in quantum machine learning. So that is why it is called hybrid. Actually, each and every time we are using classical computation to improve quantum accuracy. So next, you need to load your data. Okay, I'll give that link. I'll give that link with you. Please download this file. Yeah, you can use in Colab, but you need to install a few commands. So I already loaded the test data and training data, right? This is the test data. So I shared two files. So go to this website. Download these two files. Are you able to download two files? Train and test. Two files. Train and test. I shared multiple times. Sorry for that. Great, great. Okay. Otherwise, you go to this website, you are able to find. Then what you're supposed to do? What you're supposed to do? You need to create this folder. Okay. You need to create variational underscore classifier like a folder. Then you need to create data as the folder like subfolder. Just like this. Just like this. So create variational classifier, create subfolder data. Okay, upload these two files. So go to your folder, click here, new folder, create variational underscore classifier. Okay, once you create it, click once again, create data as a subfolder. Are you able to follow? Are you able to do? Then upload these two files. Maybe I will put in chat box. Create variational classifier, create a folder named variational classifier, create a subfolder named data. Upload to downloaded files in data subfolder. Parity test.txt. Parity train.txt. Are you able to follow me? Are you able to download those files? Able to create two folders? Able to upload? Hello? Okay, okay. I will wait. So go to your QBride, click files. So click this icon. This will create new folder. If anybody completed, please put message in chat box. Please look at the names carefully. So don't make any mistakes. Better you copy from that website. They given clearly. You copy this to rename your folder. Anybody able to download? Anybody able to create folders? If so, please put in chat box. Okay, great, great, fine. So next what we do, we try to load data. We try to load data from our repository. So I will hide this. So what we are doing, we try to load data from this parity train.txt file. Okay, the data type is almost integer. Okay, we are loading for data variable. So here we are splitting data, okay, into two category, one for capital X, one for capital Y. And for capital Y, we are shifting from 0, comma 1 to minus 1, comma 1. So we are converting the base state over here. Then we are using zip function in Python to combine these two values. So you can see the basis x-axis, x value and y value. Okay. So successfully we encoded our data into two variables. Anybody able to run this? Anybody able to run this? Anybody able to load data? Okay, great. Okay. Some of you able to do. So next what we do, we try to create randomness. So we try to create randomness. That is why we are using seed function. Okay. And we are try to add weights and bias. We try to add weights and bias. So copy this and try to run. Now what happened? The number of qubits is 4. The number of layers is 2. And how we want to compute our weights with the help of this formula. So 0.01 multiplied with a random value from number of layers, number of qubits, 3 levels, and required grade is equal to true. So all this function call able to create some random value multiplied with 0.1 assigned for weight initialization. In the same way, we are creating for bias value. Are you able to get? Are you able to get? Okay, great, great. So next what we do, we try to create optimizer. Okay, it is a classical optimizer. It is not about quantum. Okay, this optimizer will give optimized value for your quantum parameter. So that parameter is called data. So we call this optimizer with input value 0.5. Okay, that is our optimizer value. Okay, now check what is the value for optimizer. It is an object. So next what we do, we turn all these classical optimizer value into prediction by converting into -1, 1. So we try to map with our input to output predictions. So we are running iteration for 100 times. So each time we try to calculate cost, we try to calculate accuracy. Okay, finally we able to achieve accuracy equal to 100%, and the cost also got reduced. So this is called minimum cost or minimum energy. Okay, somebody asked before. So quantum always want to find its minimum energy. So this is how we did. So each time we are doing optimizer step by step. We are loading our data. Okay, so we are creating 2 batches. All right. So we are calculating cost, weight, bias. Okay, batches, everything we go for step by step initialization. Okay, so each and every time what we do, we try to find prediction, and we try to calculate what is the current cost of this entire step. Okay, then we try to compare the prediction with the actual one. Okay, then you can able to find the accuracy. Okay, we are doing the same thing for 100 iterations. So next what we do, we try to compare with test data. So we trained our model with the help of all these input parameter and using the variational classifier. Then what we do, we try to do with test data. Let's see how it is performing. So we are loading data from parity test.txt. Okay, again we are doing the same thing like training data. Okay, we are using variational classifier for test also. Okay, and what is the prediction? The prediction is almost about 1. Accuracy and unseen data. If you are providing new data also, it will predict in exact way. So this is a little demonstration how you can do quantum variational quantum circuit to do prediction. Okay, in the same way you can look for second example, iris classification. Okay, please go through this code. Data also given. Okay, so this is how you can do simulation in penny lane. So if participants having any doubt, they can put in chat box. And if you want to know penny lane documentation, I'll share this link with you. Recorded videos are uploaded in YouTube. Please go and check that link. I hope everybody able to see. The chat box is not enabled. I will answer one by one. So many questions. So many questions. We can stop, but for namesake, we are doing for 100 iteration. We don't know when we'll have convergence. Yeah, we can visualize. We can use draw function. It is available in penny lane, just like Qiskit. We able to visualize. How gates are connected in quantum circuit? Normally, it is a logical view, but if you go for physical, each and every qubit topology will differ. Even if four friends are standing in the same line, okay, if they have different heights, okay, there is a different combination of their sequence, right? So if they are standing in their as per their height, okay, the view will be different, the performance will be different. Okay, the same apply for quantum also. So it is about more and more hardware perspective. We need to calibrate. So how efficiently we can organize qubit next to next? This is very open question. Very good question. How to fix the iteration tuning method? Same, whatever you are using in conventional, you can use the same logic in quantum. Sometimes it will work. So there is no clear cut answer for this. The classical ML is entirely different from QML because classical ML, we are dealing with classical data. Okay, what is the problem with classical ML? If data is very huge, okay, not only about the data, the computation is very complex. Then whatever the supercomputer if you are using, it will not give the expected output in shorter period of time. Where in QML, it is comparatively easy. Okay, exponentially it will do operations because of quantum parallelism. So many precautions are required. First, we need to understand how it is working classically and how efficiently we can convert into quantum and which platform it is suitable. For some cases, ansatz will be suitable. For some problems, quantum annealing is suitable. For some problem, quantum gate-based operation is suitable. So there is no single answer for this question. Yes, it is done through classically, and we are feeding to the quantum network. Qiskit is the entire framework. They have their own computing fleet. Penny Lane, it is very open source and they are allowing all vendors. So from Penny Lane, you are able to access Qiskit IBM system. You are able to access Microsoft quantum system, able to access Google system, most probably Amazon. Okay. So Penny Lane have wider variety in case of hardware access. So both you can use. Penny Lane is more suitable for quantum machine learning. Now they are pioneering. they have very beautiful documentation, even when compared to Qiskit, I supposed to say. We cannot store quantum data. During the process, we are able to compute, but when you do measurement, you will lose. We cannot store quantum data. Converting into quantum state is different. Okay. During process, storing your quantum state is different. Yes, you can use image-based dataset. Quantum image processing is a different topic. Qiskit have a separate package. PennyLane have separate package. Please go for it. To understand quantum machine learning or quantum image processing, we need to have solid foundation about quantum computing. So probably it will take 6 months to 1 year to have solid foundation about quantum computing. So anybody want to directly jump into quantum machine learning or quantum image processing, they feel quite difficult and challenging. Yeah, in PyTorch also quantum packages are there. TensorFlow also quantum packages are there. They are supporting for hybrid approach. So that is why that is how I showed. Okay, the binary data is encoded into quantum state using that rotational gate and C naught. Please go and refer that code. There is no PennyLane equivalent from Indian vendor. Yes, we are writing a small kind of platforms. Even CDAC developed QSIM before 2 sessions. Before last session, I introduced right QSIM and QC tool. Okay, thank you for all your queries. I hope I gave a simple glance about quantum machine learning, which is quite tough. Thank you all for patiently listening, interacting with me.
Thank you, Mr. Dr. Jaykumar Vaidya. The questions, as we know, we can clearly understand the interest of everybody. And thank you very much for the slow pace at which you went, so that many could try and look at that. Yeah. So, Ashish sir, you can conclude today's this thing. I would like to make some announcements regarding the quiz after we conclude, and we thank Dr. Vaidya. Yeah.
So, thank you, sir, Jaykumar, sir, for this wonderful session on these advanced topics, specifically related to these quantum machine learning and what kind of error control methods and how it can be basically differentiating between the classical computing with respect to the classical machine learning with respect to this quantum and all. So I hope participant will get a clear idea and insights about these technology and concepts, and accordingly they are parallelly asking the questions, and Jaykumar sir is effectively handle all the questions. And as I can see that no more question is there, so let's conclude this session here. So thank you so much, sir, for joining and
Thank you, sir.
giving,
Thank you.
giving these such beautiful and awesome concepts to the participants. And once again, I